Okay, so we talked about the wave-particle duality of electrons and other quantumly small objects. In 1924, de Broglie proposed that particles could have wave-like character in addition to their particle character. And so we see this wave nature of an electron most clearly in electron diffraction. And so this is a lot like the double slit experiment we saw, the guy on the beach with the box. And so we see an interference pattern when we shoot a beam of electrons through two slits. But what's important and also disturbing is that the interference pattern is not caused by pairs of electrons interfering with each other, but a single electron interfering with itself. Because it's a wave. A wave interferes. When a wave goes through slits, it diffracts and interferes. A single electron is a wave. It can go through two slits and interfere with each other, with itself. It's disturbing, right? This is a very troublesome chapter. So the proof of this came in 1927. So here's the electron diffraction. So just like with the light, we have a source of radiation, so it's the electron beam. We've got two slits, and what we observe on the detector, we don't see a screen, but there's a detector, we see an interference pattern much like the dots of light that the guy saw in the box, right? And this is from electron waves interfering with themselves. If the electrons were behaving as particles, we would just see two bright lines. So the electrons that came and hit the slit would go through and be detected over here, and the others would bounce off. So this is how a particle would behave. Bless you. This is how a wave behaves. So the wave nature of the electron is an inherent property of individual electrons. And so the de Broglie relation describes the relationship between the wavelength and the frequency for a particle. So we saw a relationship between wavelength and frequency for electromagnetic radiation. Right? For light, we saw that the frequency is equal to the speed of light divided by the wavelength. This was for light. Here, or we could write it, yeah, so just forget that. That letter, what is that letter? Is it nu or V? It's V. I fooled myself and got started talking about frequency. Okay, so V is velocity, nu is frequency. That is an italicized V. I know, right? So it's not the best presentation there, but trying to show you there is a very slight difference between V's and nus, right? So this is an italicized V. That's a regular V velocity. So the convention in equations is if it's a variable, it's italicized. If it's a unit, it's not. This is the Greek letter nu. That's the italics version and the non-italics version. And that stands for frequency. They look extremely similar. It's unfortunate.
Is there something that you do when you write them that makes them?
So, handwritten V, nu.
Okay.
Yeah. So the nu, this is supposed to be straight, and then what I'm thinking about is more difficult. And then this is supposed to be curved. It's got a little tail to it. And the V, try to just make it straight.
Yeah.
I think either too much caffeine or not enough caffeine. That one's not very straight right there.
If it's attached to an M, is it okay to assume that it's a V
Right, so here we have mass and velocity, and that shows up in like kinetic energy, mass velocity squared. Yeah, so it is unfortunate. It's unfortunate. I just, I don't know what else to say. At least I didn't use a Japanese character or something. That would be harder, right? At least these resemble things we're familiar with. So there's context. And the good news is I am not going to try to trick you with the difference between frequency and velocity. Okay? And if you come to me during an exam and ask me, is that a V or a nu? I'll tell you, right? Because this is not something that we need to worry about too much. But the de Broglie relation up here, and most of these equations will be given to you on an exam, relates the wavelength of a particle to the velocity and the mass of the particle. And the reason that works has to do with kinetic energy is 1/2 mv squared, and then you've got frequency and speed of light versus, all those other things. But we are not going to worry about that. H here is Planck's constant, the same as H was before. So that's nice. So what's the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume that this length is 1.2 times 10 to the minus 10 meters. I'm going to trip on that chair. Well, what are they giving us here? They gave us a wavelength. So that's 1.2 times 10 to the minus 10 meters. Always write your units. Have I said that before? Yes, I have. I'm going to say it many more. Always write your units. Asking for the velocity. And so we're like, what do we do with this? Well, de Broglie wavelength, maybe we need the de Broglie relation. So lambda is h over mass times velocity. And so we can rearrange that equation. Velocity is h over the mass times the wavelength. Some of you are still struggling with rearranging equations like that. Please ask me for help outside of lecture. Okay? You can get better at it. Well, what's h? Planck's constant. That's why it has a name, because Planck's constant is easier to remember than 6.626 times 10 to the minus 34 joule seconds. The only reason I remember that is that I keep using it. And down here, I need mass. Mass of what? The mass of an electron. Let's see if she behaves better today. Hey Siri, what is the mass of an electron in kilograms?
Just a moment. The answer, lost the connection. Let me try that again. The answer is 9.109383632 times 10 to the negative 31 kilograms.
Yeah, Alex, I asked it a slightly different question. Hey Siri, what's the mass of an electron?
The electron is a subatomic particle, symbol or Greek letter beta, whose electric charge is -1 elementary charge. Do you want me to keep reading?
No, thank you. No, I've got it, but yesterday I was asking what's the mass of an electron. She keeps telling me about an electron, but she doesn't tell me what the mass is. So, looking stuff up is helpful, but sometimes it's easier to just look in the book. And then 1.2 times 10 to the minus 10 meters is the wavelength. The unit on the mass here needs to be kilograms, and I won't be trying to trick you on this one either, but a joule is a kilogram meter squared per second squared. And so we need kilograms for the mass. So this is going to turn out to be in meters per second. Yeah, the velocity here is always going to end up in meters per second. That doesn't seem right. No, it isn't. Yeah, I entered a number wrong. I had 10 to the minus 10 on Planck's constant. Don't know why. What? Oh, jeez. I was trying to fix it, and I just need to start over. It's always a good idea to clear the calculator and type it in again. Because then either, if you get the same answer, either it's correct or you're really consistent about making mistakes. That sounds better. Is that a reasonable speed for an electron? How do we know? Well, in general, the smaller the object, the faster it moves. The larger the object, the slower. So we know that electrons are incredibly small, and so we would expect them to have a fast velocity. If we ended up with times 10 to the minus 6, then we should question our calculations, right? Because I can walk faster than that. So here's a thinking question. Since quantum mechanical theory is universal, it applies to all objects regardless of size. Therefore, according to the de Broglie relation, a thrown baseball should also exhibit wave properties. Why don't we observe such properties at the ballpark? As an open-ended question, this would be very challenging for a 1A student. But it's multiple choice, so we should be able to evaluate these three choices. Because of the baseball's large mass, its de Broglie wavelength is minuscule and insignificant compared to the baseball's size. Well, is that true? The wavelength is equal to h over m times the velocity. So if the mass is big, what does that do to the wavelength? Makes it really small. So, if a baseball is, 2 inches across, and its wavelength is like 10 to the minus 15 meters, would you be able to see the wavelength? No. You're not going to see a baseball, how to make it look like a baseball, I don't know, that's going up and down as it's flying, right? We don't see that. But what if its wavelength is so small that we can't see it? Is that possible? Yeah, that's possible. So letter A might be correct. B, since baseballs do not have any charge, quantum mechanics does not apply to them. Well, we've just been talking about electrons. Do electrons have charge? They do. But do atoms have charge? No. Does quantum mechanics apply to atoms? Yeah. It says right up here, it's universal. So this can't be true. Quantum mechanics does not apply to baseballs. No, it's universal. It applies to everything. It's like, well, it doesn't apply to baseballs, but it applies to golf balls. You know, just random. So on a multiple choice test, which most of the test is multiple choice, you can use test-taking strategies by evaluating the possible answers, and a lot of times you can eliminate a couple of them at least, and then remember you're going for the best answer, and sometimes it's not exactly the correct spot-on answer, but you're just going for the best answer. Any questions about this one? The uncertainty principle. So when you try to observe the wave nature of an electron, you cannot observe its particle nature. If you try to observe its particle nature, you cannot observe its wave nature. So the wave nature is the interference pattern we see in the diffraction, and the particle nature is identifying which slit the particle goes through. And so these two properties are complementary. We cannot observe them both at the same time, and the uncertainty principle says that the more we know about one, the less we know about the other. It's kind of like life, you know. You can't win, you can't have it all, and then sometimes even the little bit that you do have gets taken away, right? Sort of a negative view of life. So if we take that same experiment where we saw the diffraction pattern and we shine a laser beam across here, the laser beam allows us to detect which slit the electron particle goes through. If we can detect which slit the particle goes through and we can identify it as a particle, it will no longer behave like a wave, and we will see two bright lines instead of the interference pattern. Take away the laser and the diffraction pattern comes back. Put the laser on, two lines. How does the electron know we're looking at it? It doesn't, but this is just disturbing. So there's a relationship developed by Heisenberg. It's called Heisenberg's uncertainty principle. I think there's a homework question or two that makes you do something with this actual equation, but in general, we just need to know the idea of this. So delta X here, that is the uncertainty in the position of the electron. So if delta X is large, that means that we only have a vague idea of where the electron is. If delta X was small, that means we have a much better idea of where the electron is. I think of my son Andrew as being a little bit like an electron sometimes, because like one time when he was 2, I couldn't find him in the house, and it turns out he had gotten out and went across the street and stole the neighbor's big wheel and rode it 3 blocks away to his uncle's house. But normally, Andrew at 2 would be in the house, right? And so you could say, well, I'm pretty sure I know where he is. Right now, I'm quite confident that Andrew is at school, but somebody else was taking him, so I don't know that for a fact. So there's uncertainty in Andrew's position. Do I know exactly what classroom he's in right now? No. There's uncertainty. But do I know he's in Reedley? Yeah. He's not here in Fresno. Then we have the mass and the delta V, that's a V, velocity. So the uncertainty in the velocity. So the product of uncertainty in the velocity and uncertainty in the position has to be greater than this weird looking constant. Exactly what that is doesn't really matter, but this is a fixed number. So that means that if I have a small uncertainty in the position, if I know where the thing is, then I have a big uncertainty in the velocity, and vice versa. So we cannot simultaneously measure the position and the velocity of an electron. And not just because we haven't figured out how to do it, but because it's fundamentally impossible. An electron is two things at one time. It's a wave and a particle, but that cannot be observed. When it's observed, it collapses into one or the other, like the dead or alive cat in the box. Any questions? Isn't this fun? So which statement best summarizes the uncertainty principle? Both the position and the velocity of an electron can be accurately known at the same instant. Is that true? No, not true. Either the position or the velocity of an electron can be accurately known at the same instant. If we can know essentially exactly where the electron is, but then we know nothing about its velocity. We don't even know what direction it was going or if it's moving at all, absolutely nothing. So most of the time we know a lot about one thing and little about the other, but we can know one or the other. We can know the velocity of the electron, but then we have no idea where it is, right? So this is true. What about C? Neither the position nor the velocity of an electron can be accurately known at the same instant. That's not true. It doesn't say neither the position nor the velocity are known. I don't know where a particular electron is right now, but can they be known? Yes. We can measure the velocity of an electron. We can identify the position of an electron. We just can't do both at the same time. Any questions?
So,
Mm-hmm.
like my very limited grasp of like quantum mechanics or whatever.
Mm-hmm.
When you have like a quantum computer, you're like, it's basically both things at once. It's like a 0 and a 1 at once, right?
A quantum computer. I'm not familiar with that term.
Uses qubits instead of a normal bit is binary, either a 1 or a 0. A qubit can be both a 1 and a 0 until you look at it, and then it occupies the same state.
Okay.
Awesome.
It's
Yeah, okay, yeah.
And they're pretty. If you want to look at a really beautiful computer, they're like shiny and like beautiful.
Interesting. I'll have to look into that. Whoops. So classical physics is what we experience. You know, you learn to throw a baseball, you learn to catch a baseball. Your brain is learning classical physics, whether you realize it or not. According to classical physics, a particle will move in a path that's determined by its velocity, its position, and the forces acting upon it. And so you can predict where the baseball is going to go. That's called determinacy. The present determines the future. Since we can't know both the position and the velocity of an electron, we can't predict where it's going to go. We can't predict its path. We can't say this is where it's going to go. Indeterminacy. The future can only be described statistically. So we can say, well, there's a high probability that the electron's going to be over here after such amount of time. But we can't predict its path like we can, say, for a baseball. So here, a batter hitting a ball, there's a trajectory for the ball. We know the size of the ball, its wind resistance, we know its mass, and we can calculate, the force with which it was hit. Here's its position, its velocity. There's force on the ball pulling it down, and we can predict where it's going to land. And this is how a decent outfielder can watch that ball coming and get into the right position and catch it. Your brain is doing all these calculations and you're not even aware of it. It doesn't work for electrons though. Not sure why they did hitting baseballs and now all of a sudden they're pitching baseballs. I guess it's just different ends of the same thing. So here's classical trajectory, determinacy, the baseball pitcher throws the ball, and we can predict its path, and the batter can hit the ball. If we do that with an electron, we can only predict that, say 20% of the time it's going to be within this region. Even if the electron was sent in exactly the same direction, same force, exactly the same everything, it would not hit in the same place every time. That doesn't happen with large objects, but it does happen with the quantumly small. And so we see there's the number of pitches versus the distance from the center of the strike zone. So more pitches are going to hit near the center of the strike zone, and as you get further and further away, the number of pitches that end up out there goes down. And so we can use statistics to say, well, there's a 90% probability that it's going to hit within this circle. But could the pitched electron go up and hit this guy in the face? It could, right? Like almost anything's possible. Yes?
So back on the slide,
Mm-hmm.
we had the image of the electrons, or sorry, I guess it's a couple slides. The slide where you had the electrons going through this, When you say operates as a wave, what kind of wave are you referring to?
Well, it would be like a sine wave, like electromagnetic
So,
radiation.
So it's just moving in one direction. It's not moving like a wave, like a wave goes
Well,
against the beat kind of thing. So
no.
I'm trying to understand.
Yeah, so water waves are nice to think about because those are waves we can actually see, and yet those are different than electromagnetic radiation waves.
Okay, so it's just a singular wave. It's not moving.
It's not this wide band of wave going
Okay.
together. Yeah.